Okay, so I'm talking today about a group that not all of you will be familiar with, the Sipunculan worms, and looking at the origin of the body plan of this, let's say, phylum. What are the Sipunculans? Sipunculans are quite simple externally. They consist of a trunk and an eversible proboscis that bears on the end a circumoral set of tentacles, normally, and they're characterised by a U-shaped digestive tract. They've long been considered as one of the invertebrate phyla. They've got a distinctive body plan that's morphologically separate from anything else. And so on that basis, yes, they're a separate body plan. But more recently, with the advent of molecular phylogenetics, there's a growing case that they're actually derived annelid worms, which sort of makes a bit of a taxonomic quandary. Are they a phylum within a phylum? They've still got their own body plan, but you can't have a paraphyletic phylum, can you? So are they just, do we demote this level of diversity to sort of a class within annelids? So the molecular data are pointing to a derived position, but the morphology hasn't quite caught up yet. This is one of the latest morphological analyses based on annelids and Sipunculans, and you can see that in pink here is a sister taxon to all of annelids. There are the Sipunculan worms with their distinctive body plan. And, well, molecules haven't got a consensus as to exactly where we're meant to put Sipunculans within the annelids, or really on annelid relationships. There's a lot of uncertainty. Should we actually be treating this with some belief? Should we believe in this morphological data? If so, this poses a bit of a problem. There's a really tidy story about the origin of annelids that's sort of been coming together from the fossil record. And if we think of the mollusks and the annelids as being sister taxa, we can think of Wiwaxiids as being somewhere around that divergence point. And you can sort of tell a nice story about these sort of externally segmented Wiwaxiids becoming the Keter-bearing annelid worms. The Sipunculans with their U-shaped gut and lack of sclerites don't really fit into that story very well. And if they really are informing us about the last common ancestor of annelids and the morphology of the early annelid group, maybe we should start thinking about other trochozoan phyla as possible sister taxa to the annelids. So the Nemerteans, for example, are proboscis-bearing worms that have some similarity to Sipunculans. Could these instead be the sister taxon to annelids, throwing out this nice tidy Wiwaxiid origin? So it's worth understanding the Sipunculans and where they might fit in. Can we use morphology to reinforce this suggestion that they're derived annelids? So to address this problem, I've turned to some beautiful fossils from Zhang. Well, I say beautiful fossils. They are spectacular, but you've got to look closely. They don't look much from a distance. These are sort of rusty worms on rusty Zhang slabs, and it takes a bit of work to get in and to pick out the detail. So this is a known specimen that's been described twice with two different genus names, but we've now got a dozen specimens or so that, interestingly, cover a range of sizes. So we've got about, the smallest specimens are about 3 times smaller than the largest specimens. So we can start to unpick a little bit about the ontogeny of this organism. Now, there are a lot of features that are a little bit difficult, but we'll start off with some of the simplest ones. So these organisms have a U-shaped digestive tract. Let's pick out here the descending portion of the tract and the ascending portion. And here we've got one in a slightly different orientation. We've got these two very clearly distinct tracts of the digestive system, and potentially here at the edge we've got the anus sort of opening out laterally on the trunk, which is the configuration that we see in Sipunculans. And as an interesting little extra, we can look at the infill of this, and this actually is sedimentologically distinct. Here's the gut itself, and you can see these are sand grain size. There's a glauconate grain in there somewhere. These are, I think, convincingly deposit-feeding organisms, and they must have been transported. These are larger grains than we see in the matrix. They've got a bit of ecological information there. Okay, let's move on. The next feature is that there's a retractable introvert, another Sipunculan feature, and let's sort of pick that out here. Here's a sort of diagram. This green section here is an introvert that's separate from the trunk, slightly narrow, and can be retracted, and we can see in other specimens different states of retraction. And here you can see the sort of spines around the edge collapsing in as the introvert's retracted. So we've got this irreversible proboscis, if you like. And Sipunculans are made up of a trunk and an introvert, so this is fitting in quite nicely. The base of the introvert is surrounded by a ring of spines. And here's the counterpart to this specimen. You can see these are quite long, reasonably robust, sometimes cuticularized perhaps, structures, a single ring around the base, and they're emerging from some sort of structure at the base, sort of like prongs along a crown. You just sort of see this, this feature coming along the bottom here. That sort of seems to be emerging from this robust structure. So, is there a similarity here in Sipunculans? Well, in adult Sipunculans, not so much, but Sipunculan larvae, quite interesting, have a very prominent ring of cilia called the metatrope. And I'm not saying that these long cuticular structures are themselves cilia, but I think in terms of their position, there's a correspondence here between the trunk and the introvert. And actually, the larvae use these cilia for locomotion. So potentially, these spines are also used in locomotion by analogy with preapulids. So potentially, we've got a functional and a positional similarity, even if there's some sort of novelty going on there. So there's a potential link to the Sipunculans here. Yes, we've got this clear band of spines in a Sipunculan larva. Okay, next feature to point out is this horseshoe-shaped structure that on the smaller specimens is on the side of a trunk. Let's zoom in, and can you see here we've got this sort of ring. It's bilaterally symmetrical. We've got little tentacular things, slightly flexible, coming off the side of it. And this isn't a radial structure. This is bilaterally symmetrical, and it's born on the introvert. And here's something interesting. In small specimens, when you see it on the lateral surface of the introvert. In large specimens, you see it at the terminal end. So we've got some sort of ontogenetic migration of this tentaculate bilaterally symmetrical structure. And here it is right at the tip on this very large specimen. Is there a parallel in Sipunculans? Well, yes, I think there is. The feeding structures of Sipunculans, they do a few different things, but they always have this bilaterally symmetrical array of tentacles coming off in a horseshoe shape. They get more complicated as they grow, but you can see there's some potential sort of basic blueprints that's shared here. And interestingly, in adult Sipunculans, these tentacles tend to be terminal. But in these larvae, these Pelagiosphera larvae, the mouth, which is sort of indicated by the pale blue circle here, is born laterally on what will become the introvert. In adults, that mouth becomes terminal. And so potentially we've got a mirroring here between the sort of the development of living Sipunculans and the ontogeny of these fossil Sipunculans. A couple of other features to pick out. So the trunk, you can just make out towards the rear, has got some annuli. Sometimes they're obvious, sometimes they're more cryptic. And some Sipunculans have sort of vestigial annulation. It's not really very common, but of course if Sipunculans are derived from annelids, annelids are annulated, so potentially we'd expect to see that in early groups. And these annulations are sometimes associated with sclerites. We often see sclerites along the trunk, which are arranged in transverse rows. These are images of the internal surface of the trunk, so this is sort of the base of the sclerites that we're seeing from below. And we can sort of see in various different preservations, you can piece together a picture. So these have got a triangular cross-section. This is at the edge of a trunk. They're often replaced by pyrites, so they're more robust than the cuticle. These are tough structures. And if you look at them in various different orientations, you can build up a three-dimensional picture of the sclerites, which are conical structures with a basal invagination. So they've got quite a distinctive morphology, which is very different from, for example, we saw sclerites on Luke's gastroctrix yesterday, very different morphology. So this is biologically useful, I think, information. And Sipunculans also, mainly on their introvert, but they do also have these sclerites that have got an equivalent construction. They're essentially slightly curved cones with a basal invagination. So in terms of the affinity, I've not discussed alternatives, I've not got time, but there are a number of features that add up to support, I think, a Sipunculan affinity. Most importantly, this U-shaped gut, which is not seen in any other equivalent group, but it's a versible proboscis armature that we see on the trunk, and this sort of bilaterally symmetrical circumoral horseshoe all builds up a nice picture of a Sipunculan affinity. Where do they fit within Sipunculans? Probably not in the crown group. Sipunculans have got this helically coiled gut. The U is twisted. We don't see that in Iotuba, and other Cambrian Sipunculans don't seem to have a helically coiled gut. So presumably this places them in the stem group, and maybe you could argue that this retention of prominent annulations is an inheritance from an annelid ancestor. So what does this sort of tell us about the origins of the Sipunculan body plan? Well, I'm maybe waving my arms a little bit more now, but I think it's interesting to think carefully about Sipunculan development. This is the first larval stage of Sipunculans. This is a trochophore larva. It's delineated into different regions by these bands of cilia, and you can build up essentially a model of where the different parts of the trochophore larva end up in adults. So this again is the Pelagiosphera larva, and you can see this metatrochal region with these prominent cilia used for locomotion is becoming a sort of prominent feature that ends up demarking the introvert from the trunk. So we can sort of see this developmental trajectory in Sipunculans. And there are perhaps overtones of this, as I've mentioned, in Iotuba. So there's you can homologize if you want the different components of the Sipunculan adult. We can use that homology model to sort of compare Iotuba with the Sipunculan developmental trajectory. And again, we've got this lateral mouth on juvenile Iotubas becoming a terminal mouth on adults, mirroring this developmental stage in Sipunculans. It's worth looking as well at the development of annelids. So annelids also have a trochophore larva that's almost identical to the Sipunculan trochophore larva. Their larvae start to look a little bit different, but they do retain this metatrochal region which separates the head in annelids, this two-segment head, from the trunk. And then adult annelids start to do complicated things and start to look very different, of course, from Sipunculans. But yeah, if we put everything on the same page, we can sort of start to maybe tell a story here. We can start to see that the larval stage, trochophores are very similar. The next stage in larvae are not actually all that different. Okay, the segments are wider or narrower, but there's a certain degree of similarity here. And you can quite easily imagine deriving a Pelagiosphera larva from an annelid larva. These, if you looked at these larvae, you wouldn't necessarily say that these were different body plans. What happens is what comes after that larval stage. So the Pelagiosphera could be derived from an annelid larva, and the Sipunculan adult morphology, essentially, we can see is an extra life stage. We're seeing in Iotuba this slightly Pelagiosphera-like morphology becoming less Pelagiosphera-like as it matures. And Klaus Nielsen's got this idea that metamorphosis essentially is a result of compressing your ontogenetic development. If you're a young organism and you look very different from an old organism, the young organism can be perfectly adapted to this environment, the old organism is perfectly adapted to that environment. As you change your morphology, you're perfectly adapted to neither, you're uncompetitive. And so squashing down that ontogenetic series into a metamorphic event can give rise to this sort of separate life stages. So what I want to suggest essentially is that we can see the Sipunculan body plan as being something that's evolved by gradual modification of a Pelagiosphera larva and then divided by a metamorphic event into something that looks very different from the annelids, but we can see similarities with the annelid origins. So this this separate phylum of Sipuncula, we can in fact see as a paramorphic addition to the annelid life cycle. And I feel like this is sort of a source of morphological diversity that perhaps hasn't received as much attention as it could when we think about the origin of body plans in the Cambrian explosion. Rather than completely separate innovations, could we in fact be increasing diversity by adding new stages to the end of body stages? You know, a lot of things have got trochophore larvae. We saw the mollusks with similar looking larvae. Could it be that those early larval stages were all over the place long before the Cambrian, and the Cambrian explosion represents the sort of extension at large body sizes of these developmental trajectories?